Example 26 is looking at ordering the keys for composite index. By changing the order of the columns we place in a composite index, the columns that make up the index, we can sometimes give the optimizer a better advantage of using certain indexes for certain queries. So we're looking at a query where we have the customers table. On the customers table, we placed a composite index based on the country, the state, and the city, similar to what we looked at. In this case, we're going to look at different ordering of this composite key. Okay, and see if we change the order of these particular columns that we made this index up, if it improves things. So our query we're going to use to test it is we're going to do a select count from customers, and we're putting on some predicates using some of our keys. We're going to pick the county ID with a greater than predicate. Okay. Then we're going to have a look at the customer state province with an equality predicate, which it really likes when we're using composite keys. And we're looking for a particular city within California, Belmont. Okay. And we're going to see if it wants to use this index. And when we did the basic with the index the way we ordered the columns originally, it actually used the index, but it ended up doing a skip scan on the index. Perhaps we can get a different access path if we change the ordering of the index. So we have some examples to try for this on 26. First one we're going to look at, we want to get, this is just a little extra file we put in. We wanted to get an idea of how many rows we have in the table. I already mentioned there was 55,500. This will actually confirm that, okay? And we want to go in and calculate the selectivity. And the selectivity is the number of, the percentage of the rows we actually expected to return expressed as a percentage from 0, meaning we expect it to return no row. You multiply n rows by 0, you get 0 rows, so it's more like a firewall than a filter. Up to 1, that means it passes all the rows. Most filters or predicates, when they're used, when the equality predicate are somewhere in between. So we're estimated by the count of rows for a distinct value and divided by the total number of rows to get a calculation for the selectivity as an approximation. And we're doing it for the country code greater than 5752777 for the state of New York, in this case in Belmont. Somewhere along the way we changed the example because I swore in the lecture, in the slide, it was actually looking for California, but I guess somebody decided to change it, but that's okay. And let's look at what this gives us. So I have an SQL Plus session up here. Generally, when I look at these, we can zoom in a bit to make them a little easier to read. It's just a terminal session. And I'll just show you, I'd already run this, so there's a little bit of the results on the screen. I'll show you what I did. When I first fire up a terminal session, I need to do dot space or environment and set the database name. I had already done it, so remembered it, but I'll type it in. Because normally, if you haven't done it, we'll say ORCL. If you do it over again, it doesn't hurt anything. Just allows us to, better than not having it done. Tells me it left the Oracle base unchanged. We got the Oracle home set up. And then I can connect with the test account we're using for these demos, which is SQLT. The password happens to be Oracle, all in lowercase, _4U, where the U is uppercase. When you do the practices, be careful with that. We'll just connect as that account, and then we'll just execute the little script file. So I could just go in and execute it. Now, when I pulled it from the document for it, I actually pulled this little script file up. Okay, this first one, and when you look at it, it says this at its name, Unfortunately, it got changed and somebody forgot to update the comment. The rem is just a comment within a SQL plus script file we can run. So this isn't really the file name. What we need to use is use the real file name. The easiest way just to check the files, I've already set to the labs directory, to the demo subdirectory within it where we have all our files. We're just going to do the explanation point, what allows us to host out and get a shell at the operating system, and then just do the ls and to have a look at the demos and see what the real name is for the one that begins with 26. So these are the ones that demo. It also does the subdirectory, but I'm not interested in that. I'm interested in the original. So we're over here. We have 2501, 2506. This is the real file name. If you try to execute the one they have in the rem statement, it just says it doesn't exist. What I want to do is paste that in the paste buffer because I don't like to do too much typing. And then what I can do is go and execute this. Once I get in the paste buffer, I need to put the add in front of it. And then if I put it in the paste buffer properly, I can just paste it out. Okay, that's the way I usually do it. It will execute it. And before I execute it, because I just logged in, just before I do that, I also like to set echo on when I'm running somebody else's script file. And what that will do is allow me to see the SQL statements and the results together, so it allows me to follow what the file is doing a little bit better. Do at, and then paste it in. Once I hit return on the echo, it's not going to like it if I put the at the end. Turn echo on, see what the SQL statement is. Hit the @ sign, paste it, and then we'll get a list. So what we discovered, as I already mentioned, there were 55,500 rows in the customers table. The calculated selectivity for this predicate is 80. Okay, it has a few things at the end, but if you round it up and treat it as a percent, it actually expects to return a good chunk of the rows. Okay, about 80% of the table. Okay, as calculated, the count of this with this predicate divided by the total number of tables. The other predicates are a lot more selective. For the one for New York, it expects to return just a little over 1% of the rows. 0.01 is 1%, so it's a little over 1% of the rows. Okay, the last one is even more selective. It's actually expecting to return 0.05% of the rows. So it's very selective, okay, on the state. And what we assumed, if they're joined with AND conditions as the equality predicates, we assume they all provide the same level of filtering. So it does it does the selectivity of the first one times the selectivity of the second one. These two, we used equality predicates to get the combined by ANDing them together as a predicate. We would just multiply their selectivity. So it would even reduce the data further. Okay. So unfortunately, this one isn't very selective. It looks like it's going to return a good percentage of the row, 80% of the rows. So we're going to see how it does this query now that we have a little bit of output. The query in example 2 is just our original query with our original index in the order we said, and we're going to take a look at the execution plan. And this will be the execution plan for this one. They decided to do this. Whoops, I grabbed the wrong one by the looks of it. Come back here. So I picked the one for 2. I needed 6. 6.2. I do that once in a while. There we go. It was able to do a skip scan. I knew it was wrong because I was expecting the skip scan. Okay, for this one. So it used the index, but it did it as a skip scan. It cost us 60, we had to look at 60 blocks in memory to return 2 rows for this query. Is there a better way of doing it? Let's see if reordering our index will help out. So in this example, not only do we have the query, but we do a little prep. We drop the original customer, county, state, city index. And then we recreated in a new order. We put the customer city first, the state province next, and then the country ID last. So we're putting the ones that we have the equality predicates first and putting the other ones last. Okay. Then once we do that, we just basically execute the same query, and then we clean up afterwards. They drop the indexes and put back. So the next time we run it, this can reproduce the same demo. Now we need to have a look at the output for that. Okay. We reduced the number of blocks we had to touch. The original number of blocks we looked at for 6.2, okay, was 60. Now the time looks the same because we ended up, it was less than we could actually measure it in our environment. But when we did this time, we took a reduction, given two that look equal everywhere else, pick the one that looks at the least number of logical blocks. And it will give you, in the long run, it will be more scale. And it was able to do it as a range scan instead of skip scan. So that means we had to look at the less of the index blocks to return the data that we actually needed for this query. So that was a very nice performance increase in that case. So next up is looking at bitmap join indexes. Not only do we have an alternate type of index compared to the balance tree indexes, we have the bitmap join indexes. We also have a bitmap index, a special type called a bitmap join indexes. One of the ways of reducing the queries in a data warehouse is to use a materialized view. To pre-join and pre-summarize data, we have to do the join and the summary at some point, but we don't do it at query time. We do it at the time we create the materialized view or we use the materialized view. By doing it at a different time than we do the query, we reduce the time and the resources it takes to do the query by using a materialized view. But the materialized views are called materialized because their data that is represented by a select statement is actually stored in a table permanently, so we can look it up joined together. The bitmap indexes allows us to store similar information in terms of a join condition, but in a more compact manner using a bitmap index. Okay, and they're called bitmap join index. And by using those, we can potentially get a cheaper query. So we're going to look at this query, which is the sum of quantities sold. Okay, and we calculate that by joining the sales and the product table as an equal join and looking for the category of CD-ROMs, our old CDs. Okay. So ROM stands for read-only media, which they were originally called. And then they came along with rewritable ones, so they're not just read once, write once, read many times. They can now be read and writ, but technology changes on people. But their original name was read-only media because they were burnt once, and then you couldn't burn them again in the past. And we're going to explore this without a bitmap index, bitmap join index, and then we're going to explore two options with two different bitmap join indexes. This is going to make an interesting example. So we'll go down and look at our demo. So first up in this one, we're going to do it without creating a bitmap join indexes, just with the regular indexes that are available on the sales and the product table that we've been using up to now. And we'll have a look at what it costs us to execute this particular query. We had to touch a large number of blocks in memory, 1,613, to return one row because it's a sum of quantity, it's a calculation. And it cost us almost 2 minutes to do it. And it's kind of amusing. These are one of the idiosyncrasies of calculating things with times the way we store time. You occasionally get a case where the CPU time is longer than the elapsed time. That's because some of these average, but then when they averaged over here, they averaged slightly differently, okay, when we did them. So don't get too discouraged. At occasion, a couple of these actually show up. Just basically, it's an idiosyncrasy of the way we actually calculate the time, okay, and sum it up. So in this case, we did a full table scan of all the partitions for the sales table. There's 28. When we did the scan of 4 of them, we were able to reduce some based on one of the predicates. And then we used an index range scan, okay, with an index on the other side to do our hash join. We filtered this one more than the sales table, okay. And then we had to do the sort aggregate to calculate the final sum, but really doesn't do a sort. And so that gave us a moderately expensive query. It's a little longer than we typically would like pure OLTP queries, even though this is leaning towards data warehousing type queries. Is there a way of making this lower cost? So we're looking to look on a variation of that, where we're basically doing the same query. We're just going to create a bitmap index, which is known as a bitmap join index. Initially, it looks just like a regular bitmap index. We just say create index. Okay, give it us a nice name that you can remember. They use BJIX as a short form for bitmap join index. And then you tell us the table you're going to create it on. So up to now, it looks perfectly okay, except for a funny name. And this is where it starts looking different. The index is going to be on the sales table, but the column we're putting it in comes from the other table that we're joining it. That's a little different. Normally we put an index on sales. Whether it be a bitmap index or a balance tree index, the column comes from sales. This is a different type of index. And then it gets even different. Then we have a from clause, which is new in index with the bitmap join in. And says we're joining these two tables, the sales to the product table, in this index. And we have a where clause that says how we're joining it. So it's an equal join based on the product ID from both of the two tables, sales and products. Okay. So what this is going to do is store knowledge about what products, okay, are for what sales in the bitmap index. Instead of having to join the tables at runtime, we can just look the information out of this bitmap join index. So the join is done during the index creation. It makes the index creation and maintaining the index more expensive generally, but it makes it cheaper at execution time. At least that's the theory. That's what we're hoping to observe. Okay. And the proof of the pudding is actually executing and see how it works. And we also put a hint on to make sure it uses our bitmap join index and did it. And then we're going to compare it to how it ran the first time. Do we see an improvement? So we have the output for 2. Now we touch 237. Originally we needed to touch 1600. We reduced the number of blocks we needed to access by an order of magnitude, which is a nice reduction. Okay. We also see some payback in the CPU time. The time to process the query is down well under a second. It's less than a quarter of a second, where before it was taking us approximately just a little under 2 seconds to process it. And now we use this bitmap index, okay, our bitmap join index, to join them together. So using a hash join, so we found a nice reduction in it. Okay. The next variation what we're going to do is really a change in the statement. There we saw an increase in performance without actually changing the SQL statement. We just add the appropriate bitmap join index. In this case, we're changing the query. We're adding an extra column, okay? So it's going to be a three-way join, okay? And we're going to look for the CD devices, but we're also going to look for the sales were done in the city of Berkeley. Okay, they're looking for how many CDs they sold in Berkeley. And we'll check to see how this performs. Okay, in this case, we had to access more blocks because we are joining 3 tables together instead of 2. And this time we ended up doing a double hash join. We were able to use some indexes, our regular indexes on them. But it would be very nice if we had a bitmap join index that did this join for us as an equal join between these two and told us the product and the city. So we would really want a composite index, bitmap index, to contain both of them. So our next example takes a look at that. We'll display it. We now go in and create a new bitmap join index. It's going to contain 2 columns, the product category from the products table and the customer city from the customers table. We just happen to be using the aliases here to make the SQL easier to write. It's a 3-way join as an equal join on these 2 columns. We didn't put the other filters. We're going to add them when we query do the query. And then we're going to see if we can convince it to use our new bitmap join index that we created on the 3 tables. Okay, and see if it will use that. So how does the output look like for this? When we go and execute it, we now reduce the output further, and we're not removed it another order of magnitude by using our bitmap index, our new composite bitmap index that we created. Very nice performance compared to the original one, and even the previous one. It was a reduction in the blocks we need to do. This is one of the original ones. This one reduced what we need by using the bitmap join index to solve the question. Very nice. Next up is having a look at tuning complex queries. Okay, so we have a complex query that we've implemented in a PLSQL block. Is going to select some information, and then based on what we got back, they're just looking at the SQL code to get the status. We're making a decision on whether we insert into one set of data or whether we insert in another set of data, depending on what we find. So we're doing a pass and doing these. Is there a way of rewriting this so we don't have to do it as 2 separate insert statements? And of course, if there wasn't, we wouldn't have bothered bringing it up, right? Makes sense having a look at it if there's an opportunity. Once again, this will demonstrate some more changes you can make. The way you write your code has a big impact on the select. So this was our original stored procedure. Now we showed you the whole thing. We're grabbing the sequence number from our select, and then we're making a decision whether we use that sequence number as part of the insert off the back, or we insert without it. So we do 2 inserts with 2 different different types of data depending on what we insert. In fact, 1 column is different between the 2 of them. Okay, and for this example, we actually didn't run it. We just wanted to demonstrate how you could rewrite it. So the second example is a rewritten version. Okay, now unfortunately this was a little different because they had it as 1 procedure. They broke it up in 2. They would still do the first one and pass in the information to it. But then we could do the insert as 1 insert instead of 2 inserts by using the careful use of the decode statement to set up the appropriate parameters depending on the two conditions, depending on what we passed in to the procedure. So it was really the two inserts we were seeing if we could replace as one, and the answer is yes, it can actually be done. And that can reduce the effort to maintain the application, because they're complex object. We use a condition, decide if we do one or the other. Now we can express it as one. You just got to get used to writing the D code and using it in different cases for SQL statements. This 29 is using materialized views. I already mentioned that. If we can write a materialized view, then we can reduce the cost. And we write the materialized views often because we have similar queries that need to be run that can be written against the same materialized views. So many times a query that either just does a sum operation without a join can be rewritten, or ones that do joins with summaries. And you can also find some that do just joins. We call them join materialized views. The ones that do both, we call them complex materialized views. The ones that just do sales are just regular materialized views. So they give them a few subnames to keep track of them. And we just want to see how these could work in our environment. So we're going to have a look at our first pass without using materialized view. So to make this repeatable, if we had have left it at the end where we had the materialized view created, we dropped it, just so we do it without the materialized view. And then we do our two queries, and we have a look at the performance of the two queries to see how they perform. And then we're going to compare them with materialized views. So this is our output. The first one we execute. It's a relatively expensive query. We need to touch 9161 blocks in memory to return just under 13,000 rows from the query. And it took us approximately just a little under 5.5 seconds. So it's getting to be a little longer query, okay? Because this one joins 3 tables together and does a summary of some of the data. And it does it as an equal join, okay, with it, then does a group guide to calculate the summary. Okay, can we do, and the second one is doing a similar thing. We're doing a join of the 3 tables, but now we're looking at different date ranges. We have some different predicates, and we're summarizing the information by grouping it by the product name and the week ending. Where the previous one was an example, we were grouping it by the product name and the same thing. So we did the same grouping, we just used some different predicates. This one was also expensive, okay, to execute. It cost us 8,823 blocks to return 500, but it actually, the execution plan it came up with, it was able to find a reasonably lower cost execution plan, because it really wasn't that expensive. It was still under a second to execute it. But can we reduce the cost? Well, perhaps we can by looking at materialized views. So we're going to create a materialized view called MV1. When you create them, you can create them with the rewrite enabled or disabled. We're going to use it, we want it enabled. And this is going to do our summary and our join condition without filtering the data too much, so we can use it in one or more cases. Now we can turn on query rewrites within our session just to make sure they occur. Okay, they're turned on now by default, but if somebody's turned them off, they need to be turned back on. But on a new database that you create in 12c, they're actually created turned on. It was actually true in 11G also. But if somebody turned them off, and then we execute our 2 queries again, and we're going to see if either or both of these can make use of our materialized view. So our output, okay, after we create it, this is just looking at the 2 queries. This time the query is cheaper. It returns the same number of rows, And it says the row source path is we rewrote it against a one materialized view. Okay, and it will be able to do a full rewrite on it. And compare it to the previous output. It was 943 in this case. We brought it down substantially in the number of blocks, and we also saw a reduction in the time. It went from 0.6 of a second to 0.16 of a second, okay, to execute this. The second query, let's see if it got advantage of it. It had additional filters on it, and it was able to rewrite it against the materialized views. It can add additional filters. Okay, it will just do a subset. In fact, what we didn't do in this case, which is also doable, if we're going to filter a lot on the ending time, we could add an index to the materialized view and ending time, and that may even give us a better access path. But even with that said, we reduced the query down to 93. Originally, it cost us for the second one 88.23, and we had a reduction in time for it. Now we got it down to 0.02. The reason why we got the reduction in time is the effort to join the tables together is done during the building of the materialized view and the maintenance, but the query gets a cheaper ride. So we just deferred the time that we do the join. It has to be done at some time. The last example in this chapter is taking a look at a star transform. Once again, a fairly advanced topic for this course, but we have a quick look at it. We've got a group of tables in the sales schema, which is a little data mart. Our fact table is the sales. It has a composite index that joins it with a number of dimension tables, and then we have the products as one dimension table. It has a primary key on it. The channels as a dimension table, and the customers. And then we're going to do a typical data warehouse query against it. We're going to look for a number of things by joining the three tables, and it's an equal join between the product ID, between the sales and the product, between the channel ID and the sales table and the channel table, and the customer ID on the customer table and the sales table. We also add additional filters. We're looking for a subset of the channels, 2 of them in fact, 3 and 4. We're looking for a particular customer city and a particular product ID is greater. And then we're going to look at some options to execute this. So let's go have a look. Should we do it as a regular join or as a star transform? So first up, we do it without any special hints to enable the star transform. We're going to do it as a regular join. We're going to have to join 4 tables in this case. And when it executes it, okay, it goes in and does the join, and we had to look at 2148 blocks in memory. It was a relatively expensive query. And we took us a little over a second to execute it. Okay. Now, can we do better than that? And this was doing it as a hash join. Can we do better with that by doing a star optimization for a join? Well, let's take a look at that. Okay. We're creating a group of indexes on the sales table. Instead of just having the composite index, we're going to add a group of bitmap indexes, one on the customer, on sales, one on the product ID, and one on the channel. We're going to enable star transform in our session. It's a dynamic parameter. Can it be enabled in the session or database wide? Since most databases are OLTP type databases by volume, it's disabled by default. Okay. And then we're going to tell it that we're doing a star transform. Even though we enabled it to allow it, we're going to hint on doing it to make sure the optimizer does it this way. And we also tell it the fact table. If the star transform would do it without the fact table, it's a less restrictive than doing it the other way. Okay, so now we're joining our tables with these additional indexes and suggesting to do it as a star transform. Then we just clean up at the end. Did it change the performance? Where is the star transform a win? When we did it, it had to look at 7811. It did it using the bitmap index, and now the joins are getting a little more complicated. And did we win it? Did either the number of blocks we needed to look at go down or the time? I think we lost a little on the blocks and we won a little on the time. So we had to do 21 here. This one did 7, so we lost on the blocks. How did we do on the time? 54.54 in CPU. 1 here, we won a little. So it's an optimization to improve the performance of a data warehouse data mart. It will actually show it here. Whether it's that much of a performance, even though we have 1 million rows in sales for a data warehouse, by today's standards, that's a pretty low number of rows. There are lots of people that might have 100 million rows in their table. And then the difference in blocks and execution time may be quite a bit more in that case. Okay, but there was a little bit of savings in time in that. Test, 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 right? So this completes this lesson. We have an interesting practice that we're going to do in another segment where we're going to look at rewriting queries for better performance, just showing you some